might be the best thing to do,
Awesome.
given you don't have any problems. Let's see, let me just make up some situations.
Sure.
What's the measurement of arc AB?
80.
No, that's a central angle.
Oh, of arc AB. Would you just do 180 minus 40 divided by 2?
No. In other words, the measurement of the arc is the same as the measurement of the central angle. That's
Okay.
also 40 degrees.
Okay.
Now, what you were thinking of is if it's an inscribed angle that cuts out that same arc, 40 degrees, then this would be 20.
Okay.
In other words, the measurement of the arc is twice the measurement of the inscribed angle. But the 20 degree is inscribed because its vertex is on the circumference. The 40 degree is central because its vertex is at the center of the circle.
Okay.
Okay? So those two things are very critical.
Okay.
Hold on, let me see if I can think of the other very common situation is, what are these lines called?
Inscribed angles, right?
No, it's not inscribed because the vertex is not on the circumference.
Yeah. Points of tangency?
Secant lines.
Oh, because it hits the... Okay.
Because
it hits circle twice, right?
Exactly.
Okay.
As opposed to a tangent line, which only hits the circle at one point. A secant line intersects the circumference in two spots.
Okay.
So when I have two secant lines here, what is that angle equal to?
So if there are two secant lines, wouldn't it be equal to 180? Come on.
No, it has to do with the measurements of the two arcs that the secant lines intercept.
Okay.
It's 1/2. The big one?
Oh, AB minus CD, right? Okay.
Okay. So as long as they give you some information, they'll always give you enough information that you can calculate the remaining. Now, very similar to a secant line is if you have this situation where you have a secant line and you have a tangent line.
Okay.
Same thing.
Okay.
What's theta equal to? In other words, this situation is no different than this one.
Right. They're the same.
So what's theta equal to?
Is equal to 1/2 AB minus C. Would just be C.
CB.
CB. So, I didn't.
By being the same as this, what I meant was that there is a big arc and there's a little arc.
Okay.
And so it's still half of the difference of those two arcs.
Okay.
Okay.
Cool.
Third situation that's similar to this is if I have, boy, how perfect is that?
That was a good one.
Can I do that? I don't even know. Okay. Now, we have a tangent line, and we don't have a secant line, do we?
No.
But that line goes through the center of the circle.
Right.
And when you have this situation, let's say they give you this angle here.
Uh-huh.
I have to extend that secant line all the way, like that.
Okay.
Okay? Now, what is theta, that 40 degrees, going to be equal to?
So that 40 degrees would be equal to 140, right?
1/2. Start everything
Or 1
off
half.
with that
Yeah, my
1/2. So
yeah,
you
1
don't
half.
forget it. But
1 half AB minus CB.
okay. Now, what's the relationship between AB and CB? The fact that this secant line is also a diameter means what's the arc length from there? What's the arc? What's the measurement of the arc AC?
The measurement of the arc AC would be
Because it's a
well, it's 180. Yeah, it's 180. Yeah.
Right. And the measurement of the arc ABC is 180 also, right?
Exactly.
So if I call that X, in other words, if I call CB X, what's AB?
Then AB would be, well, that'd be 80, wouldn't it? Well, no, because it's
180 from A,
180 minus X
there you go.
is equal to, oh,
That's
yeah,
it.
just like that. It's equal to 40.
Well, no. Arc
Well, yeah,
AB is 180 minus X.
Yeah.
And arc CB is X.
Right.
So if I'm going to take arc AB minus arc CB, this is what I get. And then you end up with something that looks like this. 40 equals 1/2 of 180 minus 2x.
Yeah.
Okay. But again, you can see the similarities. All so far, everything that involves an intersection outside the circle is 1/2 of the difference of the two arcs.
Yeah.
That are intercepted. But when one of your secant lines happens to be a diameter, well, now you know that the two arcs add to 180. So I can list both of these things using one variable only, which is x. And the advantage of only using one variable is now I have a full equation with one variable. I can solve it for x. And I'll be able to solve for the little arc and the big arc once I come up with x.
Okay.
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 Another situation.
Cool.
Two tangent lines. Intersecting outside of the circle.
Okay.
It's supposed to be tangent line. What's theta equal?
Oh, that looks good. So that'd be equal to 1/2 AB minus CB.
Well, not quite. State it again. Based on my new lettering?
Yeah, so 1/2 AB.
Not AB. Because
would it be just C?
Because I have a third point that I've put on there, it's 1/2 of the big arc, which is ACB.
Oh, okay.
Minus the little arc, which is AB.
That makes sense. Okay.
And it's definitely a littler arc. In other words, the big arc is greater than 180 and the little arc is less than 180, always, when you have two tangent lines like that.
Right.
So, so far, all of these things are pretty much the same. They're all intersecting either secant or tangent lines outside the circle.
Yeah. And
we can figure out the measurements of these intercepted arcs that way.
Okay.
Now, let's talk about when you have just two chords that intersect inside the circle.
Okay.
There's a couple of things that happen here. the relationship if I wanted to know the measurements of these chords? Let's say I make that one 4, this one's 6, that one's 7. What's x?
So x would
is involved.
So
straightforward. The one piece of the chord times the other piece is equal to 6 times 7.
So 4e is equal to
4x is equal
4x.
to 42.
Yeah.
So I
makes
solve
sense.
for x. But
Yeah.
the key part of this is that AE times ED equals CE times EB.
Okay.
No matter where the chord is, as long as it's two chords intersecting inside the circle.
Okay.
Okay? Now, there's another formula or theorem regards to these chords that has to do with the measurements of the arc lengths. In other words, that formula was for the measurements of the chord segments, but if I know theta, what is the relationship between theta and the measurements of the arcs around the circumference? Theta is equal to 1/2
of AD.
Which one?
Would it be AB and then CD, right?
No, it's the
Or would it be AD and then CD?
It's BD.
And then
In other words, you have to look at which arcs are intercepted by that angle.
Okay.
Okay, they're BD,
and then AC.
AC. And because I'm inside the circle, I'm going to add them.
Okay.
And that's one way to memorize it, is that when you're inside the circle, you're adding those arcs. When you're outside, you generally are subtracting them. And this also is theta because they're vertical angles.
Right.
So either of these angles is equal to this formula. So what if theta was here? What's that theta going to be equal to?
So that theta would be equal to AB and then CD because it's
Plus CD.
plus CD.
Okay.
Cool.
So those are two theorems regarding chords that intersect inside of a circle.
Okay.
In other words, I have ways of measuring the measurement of the arcs, and also the measurements of the chord segments.
Okay.
Okay? And those are the only formulas I know for chords that intersect inside. Here's another one for secants that intersect outside.
Okay.
And this, so far, everything we've talked about has been the angle and the measurements of the arcs, right?
Yeah.
Well, there's also AB times AC equals what?
AE times AD.
Yeah.
Cool.
And notice that this is not the same as chords.
No.
Chords, it was one segment times the other segment. This is one segment times the entire segment.
Okay.
Equals the part of the segment that's outside the circle times the entire length of the secant line. Okay? Now, if I change this just slightly so that I still have a secant line, now I have a tangent line,
Yeah.
What is the equation that governs this?
Um,
And it's actually, you can figure it out from the first one. So
okay.
it's AB times AC equals what?
Is equal to 80 times
Times what? That's the part of AD that's
DC.
outside the circle.
Would it be DC?
No, there's no DC,
So,
no
no.
straight line DC. It's times the length of the full segment, times AD.
So, ABCD.
No, times
Or
AD.
just AD. Yeah.
You see why
Okay.
these are the same? In other words,
Yeah.
in the first case, we had the part that was outside the circle times the entire secant
Okay.
equals the part that's outside the circle times the entire secant.
Mm-hmm.
Well, in this situation, there's the part outside the circle times the entire secant. There's the part outside the circle. There's the entire tangent line. So
Okay.
this one is usually given as squared.
Mm-hmm.
But if you forget, you can always use the same logic.
Cool.
So if that's 5, that's 4, and that's x. What equation applies?
So it would be 4 plus yeah, so
It's
4 plus
part
x.
outside the circle times the entire secant line. So write that first.
Okay, so it'd be AB or
4.
wait. Yeah, so 4 is equal to.
No, 4 times what?
So it's 4 times the parentheses. So it'd be 4 times x.
No, that would be if I had chords. In other words, remember this is distinctly different than chords. In chords, it's this times that equals this times that.
Okay.
And it's not that way with stuff intersecting outside the circle. It's this times the whole thing. Well, what's the whole thing?
AD.
Using my numbers and variables. The whole
So
thing
just
is
5.
AC. What is its measurement?
So the whole thing is AC.
4 plus x.
Just 4 plus, yeah, 4 plus x.
So I have 4 times 4 plus x equals 5 squared.
Right.
Or 5 times 5.
Yeah.
Okay. So
that'd be,
yeah, I know you know how to solve that. That's a simple equation.
yeah.
Solving it isn't the problem. Making sure you set it up, set the equation up is the problem.
Yeah, exactly.
You're not going to make your mistakes solving that. You're going to make your mistakes not setting it up properly.
Yeah, exactly.
If you make mistakes. I'm not saying you're going to make mistakes, but
yeah.
Okay, let's see if I can think of any others.
Cool.
Let me get my geometry book out. Turn to this chapter to see if I'm forgetting anything.
Sure.
Hold on.
Sure. Okay, no problem.
You got to be almost done with chapter 10, right?
I think we are, yeah.
I'm being quizzed on chapter 10. The only thing you're going to be quizzed on probably for the rest of the year, my guess, is a review of the whole semester.
Yeah, exactly.
If you get that review material, make sure you get it to me.
Yeah, definitely. I think he's getting to us, or getting that to us, like, this week sometime.
Okay.
Yeah.
So,
because I know, because finals is just around the corner, so.
Okay, there is another one I just remembered.
Cool.
There is when you have two tangent lines. What is true?
Would you just say 3x is equal to 2x minus 1?
Correct. In other words, two tangent
Just set them
lines
equal.
that intersect outside the circle
always equal to each other.
Always equal to each other.
Cool.
What's the measurement of that arc?
That'd be 120 because it hits the
Good.
circle, right? Yeah.
Well, here's the way you can think about this. You certainly know
Okay.
that angle is 120, right?
Right, yeah.
Those two angles are supplementary, and the entire circle is 360.
Mm-hmm.
And these two angles intercept the entire circle. In other words, they intercept this part, and the 120-degree angle intercepts the rest of it.
Yeah.
So you know that if these two total 180, these total 360, then this measurement of that arc is always going to be twice what that angle is.
Mm-hmm. Okay.
Okay.
Cool.
That's one of them. And hold on a second. Let me just kind of look at some of these theorems.
Sure.
See, I can't even draw the straight line as good as I can draw the circle.
No problem.
That's funny.
That is funny.
What's
That's the same thing for me. I can draw a perfect circle, but
probably draw
yeah,
a perfect
just
straight line and probably can't draw a circle perfectly, I bet.
Yeah. My circle looks like a triangle. My line looks perfect, right?
A straight line looks like a roller coaster track.
Yeah.
So what's that angle?
90.
Correct. Tangent lines connected to radius lines always form a right angle at the point of tangency.
Cool.
I'm just going to go through it page by page and make sure I have not omitted one of these. That's important.
Sure. Definitely.
What's true about if I have a chord? Jesus. Later in the day,
No problem.
straight lines. If that chord is equal to that chord, what is true about this circle?
AB is congruent to CD.
The measurement of the arc.
Measurement of the arc.
In other words, when you say AB is congruent to CD, you're basically just telling me what I wrote. In other words, when I drew the hash mark, because AB could be that chord.
Yeah, exactly.
So you don't want to say AB is congruent to CD. You want to say the measurement of arc AB is congruent to the measurement of arc CD.
Okay.
In other words, these arcs are also congruent.
Okay, cool.
Okay. What happens if I have a chord and I form a perpendicular line? What happens to that chord?
So if it's a perpendicular line.
Yeah, as opposed to a line like that.
Yeah.
In other words, if I draw the radius perpendicular to the chord, what happens to the chord?
The chord gets divided, right?
In two. Equal.
In two, yeah.
In other words, it gets bisected.
Yeah. Cool.
Always.
Cool.
big chapter with a lot in it, actually.
For sure.
Okay, here's, these problems are always kind of cool. Let me make sure I've done it correctly.
Sure.
AB is not parallel to CD.
Okay. AB is not parallel to CD.
Well, I haven't asked yet. Which angles
Okay.
are equal?
So wouldn't B be equal to D? Like,
If AB was parallel to CD, it would be.
then, okay.
Because then we'd have parallel lines with a transversal. And
Yeah.
2 and 3 would be alternate interior angles, which are congruent.
Right.
But if AB is not parallel to CD.
So what if 1 and 2 be equal to each other, and then
Why is 1 equal to 2?
because they're supplementary to each other.
No? What do they do? What kind of arcs do they intercept?
They're perpendicular to each other.
No?
No, because it's not a right angle.
What arc does angle 1 intercept?
Angle C.
What arc?
Would that be CD?
Okay, to figure out what arc an angle intercepts, just go to the rays and go to the end point of the ray. There's one ray, it ends right there.
Oh, right.
Other ray ends right there.
Yeah.
So it intercepts arc BC.
BC, yeah. Okay.
Okay? And we know that angle 1 is, what's the relationship between it and arc BC?
It's it's double. Yeah, 1/2.
Yeah, the arc is double the angle. In other words, if angle 1 was 40 degrees, arc BC would be 80.
Exactly.
Okay. Well, what arc does angle 2 intercept?
BC as well.
So therefore it has to be the same as angle 1.
Right. Yeah.
Because BC is not changing.
No.
And if, in other words, the problem is that when you have a circle and you have multiple angles that intercept the same arc, they're the same angles.
Okay.
Okay? And it's a little different than parallel lines. In other words, like I said, if AB was parallel to CD, then you would be correct. Angle 3 would be equal to angle 2, but also angle 1 would be equal to angle 2.
Exactly.
If these were parallel, all 4 of these angles would be the same. 2 of them would be the same based on parallel lines, but 2 of them would be the same based on the fact that they intercept the same arc.
Right. Yeah.
Those are the fun problems because usually they involve complicated figures like this where you have multiple arcs being intercepted.
For sure.
You want to do a half an hour tonight or an hour?
We could do either. Whichever would work best for you.
Well, since you don't have any material, why don't we just do a half hour?
Sure. Yeah.
And let me just see if I can find anything that I haven't covered yet.
Definitely.
Let's take another minute or two.
Cool.
If I have a quadrilateral inside of a circle, it doesn't have to have any right angles at all.
No.
What's true about those angles?
Well, they all have to add up to 360 since it's quadrilateral.
What else?
And then the opposite angles are Aren't they equal to each other?
No. But they are something. They're just
they're
supplementary.
Supplementary, yeah, I was just going to say that.
They add to 180.
Right.
So 1 and 3 adds to 180, and 2 and 4 adds to 180. So if I told you that 1 was 100 degrees, you know that 3 is 80.
Exactly.
Okay.
If 2 was 20, then 4 would have to be 160.
Right.
Okay. Cool.
Okay, let's see. I've covered that. Covered that. Covered that. The section 10.6, the equations of circles. I noticed that most people have a couple of questions regarding equations of circles.
Yeah.
Did you cover that?
I think we have, yeah.
Okay. The most important thing you need to know is the general equation of a circle.
Okay. Like for circumference or?
No, the general equation of a circle.
Okay.
It's x minus h squared.
Mm-hmm.
You know the rest of it?
I'm not familiar with this one.
Plus y minus k squared equals r squared.
Okay.
Okay? So, here's the question. If I have a circle, and what h and k are the coordinates of the center.
Right.
Okay?
Okay. So,
let's say I have a circle that is centered at 3, 3.
You would just replace h and k with those.
And
or would you...
tangent to that, what's the equation of that circle?
So it would be 3 minus h squared.
Hold on. Not 3 minus h. H is 3.
So h is 3. Okay.
3
is plus
squared.
Plus y minus 3
squared
is equal to, the radius would be 3 squared.
Good.
Cool.
So that's the equation of that circle.
Okay.
And it's not really very complicated as long as you know that. You must have that memorized.
Right.
If you have this memorized, you'll get all these questions right.
Cool.
If you don't have it memorized, you'll get none of them right.
Okay.
That's how important. And there'll probably be a couple questions on the equation of a circle.
Yeah, probably.
Okay? If the circle is at the origin, if the center of the circle is at the origin, then the equation just becomes x squared plus y squared equals r squared.
Okay.
Because if it's at the origin, h is 0 and k is 0.
Right.
All right.
Cool.
That's probably a good review for tonight's session.
Yeah. Definitely,
and
yeah.
Hopefully by your next session you'll have your review material. And
hopefully, yeah.
Make sure you get that to me.
Definitely,
we'll definitely want to go over that because we've been working on circles now for 3 weeks.
Yeah,
and
exactly.
Your geometry final is going to be on a lot more chapters than just this last one, the circle.
Right. Yeah, it's going to be on a
cover quadrilaterals and all kinds of stuff. Whatever you've been doing since January.
Exactly.
So, and that'll be tough for me to review without you giving me the review material.
Uh-huh.
Okay. Dylan, you have a good evening, and I will talk to you next time.
That sounds good.
All right.
Thanks, Mr. Cowan.
Bye-bye.
Okay.